In part 3 of the Unit 4 notes, we will be covering the dual wave particle nature of light and the atomic emission spectra. In the photoelectric effect, electrons are emitted from a metal surface when light of a certain minimum frequency shines on the surface. The wave model of light predicts that, given enough time, even low energy, low frequency light would eventually build up enough energy to eject electrons. This does not match what is observed. In reality, electrons will not be ejected no matter how intensely or how long the light shines if a minimum frequency has not been met. In our diagram over here, you can see the photons of light coming in and interacting with the surface of the metal, and if there is a sufficient frequency, the electrons are being emitted from the surface. In 1905, Albert Einstein proposed that light has a dual nature, meaning it can have both wave-like and particle-like properties. It can be thought of as a beam of bundles of energy called photons. Einstein also proposed that the energy of a photon must have a certain threshold value to cause ejection of an electron from the surface of a metal. Thus, even small numbers of photons with sufficient energy will cause the photoelectric effect. Einstein won the Nobel Prize in Physics in 1921 for this work. For our first checkpoint question, what could be changed in the simulation in order to produce a current? So this is a PhET simulation which we'll be running for one of our labs. You can see the intensity up here, which is essentially how bright the light is, and we also have the wavelength shown right here, which is currently 400 nanometers. Now, if electrons were ejected from this metal, they would be traveling from one side to the other across this area right here. Now, if I change the intensity or how bright the light is, that light still will not have sufficient frequency. We know from one of our previous videos that by changing the wavelength, I would change the frequency. So if I want my frequency to increase, I need my wavelength to decrease. So I would need to move this slider further to the left. By moving this to the left, here you can see that we changed it to 144 nanometers. I now have a stream of electrons going from one side to the next, and I have a measurable current which is showing up here on the bottom. So changing intensity would have no effect. You must decrease the wavelength. By decreasing the wavelength, I will increase the frequency and the amount of energy that the photons can provide. The light in a neon sign is produced by passing electricity through a tube filled with neon gas. Neon atoms in the tube absorb energy and become excited. These excited atoms return to their more stable ground state by emitting light to release that energy. So here we have two pictures of Bohr model. So here we have a standard Bohr model for neon, which could be considered the ground state. We have 2 electrons in the first shell and 8 electrons within the second shell. In the excited state, our inner cores are still going to remain the same, so I have 2 in this inner core. But for my outer core, I'm going to have at least 1 electron, this electron right here, which is going to be promoted to a further state. The further away my electron is from the center of the nucleus, the more energy it has. So as the electrical current is provided to neon, it's going to reach this excited state, it's going to absorb the energy, and then it is going to fall back down to the ground state and emit that energy in a different form. In this case, it's going to be emitting the energy in the form of light, which you can see here. The ground state is the lowest energy state for an atom. When drawing a Bohr model, the electrons will be in the shells that you would expect them to be in. For the excited state, this is a higher potential energy for an atom. 1 or more electrons will be found in shells further from the nucleus than expected. To keep things simple for our class, we will take 1 electron from the last shell and bump it up only 1 level. In reality, there can be many excited states for each atom. So for our next checkpoint question, we are going to be drawing the ground and the excited state for nitrogen. So we're going to start with nitrogen in the ground state, and then we are going to draw nitrogen in the excited state. Now if I look at the periodic table, I can find the atomic number for nitrogen. Nitrogen has 7 protons. The total mass of nitrogen would round to 14, so 14 is our mass number. The total mass of 14 minus the protons shows that I have 7 neutrons. Because this is neutral nitrogen, it doesn't say anything about it being a charged ion. I could assume that the electrons are also going to be 7. I'm going to fit 2 electrons within my first shell, and the remaining 5 are going to go into the second shell. Remember, for our Bohr models, even though you would typically find them with the actual dots representing the electrons going around the outside, for our class we're going to draw them with just numbers inside of the little semicircles, so that's a little bit easier to read and to write. Now for the excited state, our nucleus is going to remain unchanged. So my protons are still going to be 7, and my neutrons are also going to be 7. For my electrons, I'm still going to have 2 electrons in the first shell, but in my last shell, I'm going to have 1 electron, which I am going to promote to a new outer shell. So nitrogen within an excited state is going to show 2, 4, and then 1 for the shells of the electrons. Fireworks show that heat energy can also be used to promote electrons to an excited state, just like electricity was in the previous example. Crushing a mint lifesaver shows that the mechanical energy can be used to promote the electrons to an excited state. A spectroscope is a device with a prism, or a diffraction grating, inside which is used to see the atomic emission spectrum for a light source. The prism breaks up the colored light you can see with the naked eye into a unique pattern, which can be used for identification similar to a fingerprint. Even if 2 substances emit the same color light to the naked eye, they can have different atomic emission spectra. So for example, here we have somebody who is looking through a spectroscope and they're looking at some neon light. Now this light is going to appear a reddish orange color to the naked eye, but if you look at it through the spectroscope, it's going to be broken down into many very thin lines. And this pattern is going to be specifically unique to neon. If you played Marvel's Spider-Man for either PS4 or PS5, you may remember the minigame which is shown below. This involves analyzing absorption and emission spectra in order to identify chemical compounds. So this is very similar to what we were looking at on the previous slide. In the image below, there are emission spectra for 3 known elements, along with an unknown mixture which contains 2 of the 3 elements. Which 2 elements are within the mixture? Use evidence to support your conclusion. So our mixture is down here at the bottom. And what we want to do is match up the lines that are shown here with lines that are in the 3 elements up above. Now if I look at strontium here, I have a line here, here, and here, and they all match with the lines that are on the bottom. So it's a good bet that strontium is likely in our mixture. But you need to check all the way across because sometimes there might be other parts that don't match. So these lines all match up here, here, and here. So strontium is definitely going to be one of the elements that is inside of the mixture. Now if I look at cadmium, it has 2 lines right here between 750 and 700, which are not present in the mixture. It also has another line right here that is not present in the mixture, although this one seems to match. If there are any of them that are not present in the mixture, that means that that element would not be there. Lithium has a line right here, which seems to match up with the one here in the mixture. That line matches up as well, here, and then straight down over here. So it appears that lithium and strontium would be the 2 elements that are present within this mixture. Here we have a few key terms that are related to spectrum. The continuous spectrum, which was mentioned earlier, is a spectrum of light having no apparent breaks or gaps throughout its wavelength range. So this would be an entire rainbow. The atomic emission spectrum is the pattern of lines formed when light passes through a prism to separate it into the different frequencies of light it contains. So this would be our emission spectrum here, where we have the very dark black spaces in between each of the individual lines. An absorption spectrum is a spectrum of light transmitted through a substance showing dark lines or bands due to the absorption of a specific wavelength. So you can see here that it is essentially the negative image of what you would have for the emission spectrum. That concludes part 3 of the Unit 4 notes. When we come back for part 4, we will be looking at the quantum model of the atom.